We're about to unravel a huge cosmic mystery, and believe it or not, the key is hidden in the sound of a passing ambulance. We are talking about redshift, this incredible tool that lets us measure the entire universe. And yeah, it all starts not with some giant telescope, but with your own 2 ears.
You know exactly what I'm talking about, right? An ambulance is coming towards you, and the siren has that super high-pitched wee sound. But the second it passes you and starts moving away, that sound just drops. It goes down to that lower woo. Well, that little shift in sound, something you've heard 1,000 times, actually holds the secret to understanding the entire universe.
So here's what we're going to do. We'll kick things off with that shifting sound. Then we'll see how that applies to light's red and blue shift. After that, we dive deep into the expanding universe. We'll even figure out how two different kinds of shifts are actually the same thing, and we'll wrap up by looking at why redshift matters so much.
All right, first up, the shifting sound. Let's really dig into the physics of that passing siren. This isn't some random trick your ears are playing on you. Nope, it's a core principle of physics, and it's got a name.
Yep, it's called the Doppler effect. And really, all it is a change in a wave's frequency. You know, how scrunched up or stretched out the waves are, and it happens whenever the thing making the wave and the person hearing it are moving relative to each other. It's that simple.
Okay, so picture this. The ambulance is racing towards you. As it does, it's literally squishing the sound waves together in front of it. They get all bunched up. That means more waves are hitting your eardrum every single second, and your brain goes, hey, that's a higher pitch. That's part one.
And then, whoosh, it passes you. Now it's moving away, and the total opposite happens. The sound waves get stretched out, like a rubber band. Now fewer waves are hitting your ear each second. And what does your brain say? Okay, that's a lower pitch. And boom, that's the Doppler effect. Simple, right?
All right, now hold on, because we're about to make a huge leap from the street corner to the entire cosmos. Because it turns out that exact same principle doesn't just work for sound, it works for light too. And this is where it all gets really, really cool.
It's a perfect one-to-one comparison. With sound, an approaching source means a higher pitch. With light, an approaching source means its color shifts towards the blue end of the spectrum. We call that blue shift. And just like a receding sound source gives you a lower pitch, a receding light source, well, its color shifts to the red end. And that's what we call redshift.
So the big takeaway here is that light is a wave, right? And its pitch is just its color. So if a star or a galaxy is moving towards us, its light waves get compressed. They get squished into shorter wavelengths, which means they look bluer. That's blue shift. And if it's moving away from us, those light waves get stretched out into longer wavelengths, which makes them look redder, and there you have it. That's redshift.
Okay, seems pretty straightforward, right? But here's where the universe throws us a curveball. A huge one. See, when astronomers look way out at distant galaxies, they see redshift. Almost all of them are redshifted. But, and this is the crazy part, it's not because they're just flying away from us through empty space. No, something much, much bigger is going on.
And this is the absolute key. Think of it this way. The galaxies aren't cars driving down a road. Instead, the road itself is stretching. The very fabric of space is expanding, and it's carrying those galaxies along for the ride. And that creates a whole different kind of redshift.
We call this cosmological redshift. Imagine a single photon of light leaving a super distant galaxy billions of years ago. As that little photon travels across the universe to get to our telescopes, the actual space it's flying through is expanding. So the wave itself gets stretched out longer and longer and longer. And the farther it has to travel, the more stretched out and more redshifted it becomes by the time it gets to us.
But wait a minute, this should feel a little weird, right? The Doppler shift we talked about with the ambulance, that's about an object's actual motion through space. But this cosmological redshift is about space itself expanding. The physics seem totally different. The math behind them is different. So what gives? Are these two completely separate things that just happen to both be called redshift? Or is there some hidden connection we're missing?
Well, it turns out there is a connection. And the way we figure it out is, honestly, it's just beautiful. It's this brilliant thought experiment involving a chain of observers.
Okay, so the secret ingredient here is a core idea from Einstein's relativity. Think about it. We all know the Earth is a giant, curved sphere. But when you're just walking down the street, it looks perfectly flat, right? For all practical purposes, on your local scale, it is flat. Well, the same thing is true for space-time. On the cosmic scale, it's this huge, expanding, curved thing. But if you zoom way in on any tiny little patch, it's basically flat. And in that tiny, locally flat piece of space, the good old Doppler effect works just fine.
So, let's run with that idea. Imagine a massive, invisible chain of people, or observers, stretching all the way from some distant galaxy back to us here on Earth. Now, because space is expanding everywhere, each person in that chain sees the person right next to them moving away just a tiny bit. That little bit of motion creates a tiny little Doppler shift between just those two observers. Okay? Now, what happens if you add up all those millions and millions of tiny little Doppler shifts, one after another, all the way down the chain? The grand total, the cumulative effect, is exactly the same as the cosmological redshift. It's mind-blowing. They're not two different things at all. They're just the same phenomenon looked at from a local versus a global perspective.
And I'm not the only one who thinks this is amazing. The scientist who actually proved this mathematically said the result is, and I quote, quite stunning. It just perfectly shows that these two effects that seem like they come from totally different physics are, at their heart, the exact same thing. Okay, so we've solved this huge cosmic puzzle. That's great for physicists, but so what? Why does any of this matter to the rest of us? Well, it turns out that understanding redshift is absolutely critical for everything, from our daily weather forecasts all the way to understanding the Big Bang itself. For starters, right here on Earth, weather radar is literally Doppler radar. It bounces radio waves off raindrops to see how fast they're moving, which lets meteorologists spot the telltale rotation inside a storm that could spawn a tornado. It's a lifesaver. Zooming out, in astronomy, redshift is like our cosmic measuring tape. It tells us how fast galaxies are moving away and how far away they are. In fact, that's the very evidence that led us to the Big Bang Theory. And today, it's still the #1 tool we use to test our wildest ideas about the cosmos, stuff like dark energy and even whether time flows the same way everywhere.
And this is how we use it to piece together the entire history of the universe. By measuring the redshift of things at different distances, we're literally looking back in time. We can map out how fast the universe was expanding at different points in its history. This graph here, for example, is testing an idea called a loitering universe, a theory that maybe the expansion slowed way down for a while. Redshift is basically our time machine that lets us see if these stories about the cosmos are true.
So there you have it. We went from the simple wee-woo of a passing siren all the way to a tool that lets us read the biography of our entire universe. Redshift has shown us our past. It's told us the story of where we came from. The big question now is, as our tools get better and our measurements get sharper, what secrets about our future is it going to reveal next?